Yo, what is going on, Astro Geeks? It is your boy Aphelion, and a lot has happened in the last week, so let's talk about it. First things first, I published some shorts because I had the opportunity to do so between episode 8 and episode 9, so I reviewed episode 1 through 4, and I clipped some of the content that I thought would work really well for shorts. And upon publishing them, they immediately racked views, and they banged views. Like the first 24 hours of me releasing it, they got hundreds of views, and I was really ecstatic about that. That made like the next 1 or 2 days of mine because I was so excited about it. And if you're coming from the short form content that I've published and you're starting to watch some of the full length episodes, I appreciate you being here and taking the time to kind of listen to the whole thing. So that is the first thing. The second thing is that upon reviewing those episodes, I noticed that I was doing a lot of verbal static, and the flow of the podcast kind of got ruined by it. Like doing that, doing in between everything, kind of it, yeah, just like it didn't make it sound as nice to listen to the podcast. It, it like, it's very difficult for me to describe it, and within, like, those are the moments where I'm kind of like, and I just want to work on not doing that and just be really concise and not sound like I'm rushing through words and being really fast, and trying to keep trying to force everything to be fast, force the speech to be fast and leave no gaps in between. Like, gaps in between aren't that bad is what I'm trying to work on learning, and I'm trying to work on doing less So that was the second thing. So let's talk about the podcast today. Today's episode is about semi-regular variables, so we are sticking very close to the last episode that was on our Corona Borealis variables, which I refer to as RCBs. It's a really long name. And this episode it's inspired by a conversation that I had with a friend. I was explaining to him the contents of the last episode and, variability of the star. And he wanted me to explain what the variability of the star meant. And I kind of went along the lines of the explanation that I gave in the last episode about stars pulsating, sometimes it's just called pulsating variables. And then you got cataclysmic variables, and then you have some other stuff in the mix. And he asked me, well, what causes a star to pulsate? Like, how do you even get to a point of a pulsating variable? And I was like, that's actually something that I'm ill-informed on, and I should probably cover. And that's definitely something on my end that I should be improving on. Because, it's as I report on these podcasts, it is my job to make all of that stuff very clear. So before we get into semi-regular variables and all of the cool things about that, I want to make sure that the understanding on pulsating variables is crisp. So yeah, let's be clear on what allows a star, let's talk more about pulsating variables and how they work before we get into the semi-regular variable stuff. So before we even get into what makes a star variable, I think it's also important to talk about what makes a star stable. So let's talk a little bit more about that. I've mentioned hydrostatic equilibrium before on this podcast, but I gave a very vague description by saying stars experience inward and outward pressures, and when they're balanced, you get hydrostatic equilibrium. But again, I want to be more specific. So a star forms as matter accretes to a specific place in a molecular cloud, right? And this matter in itself creates the gravitational force of the star that pulls the star inward. Now, if that's a little bit difficult to grasp, I would say the easiest way to understand why that is true is to apply a bit of a tweaked version of Newton's law of gravitation to this situation. You've got a lot of mass with very little distance between each other when a star forms. And so that will increase the force of gravity in that spot, right? Like Newton's law of gravitation, when we write it, is usually we're looking at two objects and the gravity, the force of gravity between those two objects. But I feel like if you tweak that a little bit and think about it a little bit more conceptually rather than looking at two objects, I think that it's still applicable, right? So again, lots of mass with very little distance in between each other will increase the force of gravity in that spot, which is the first pressure that we define in hydrostatic equilibrium. It's the force of gravity pushing the star inward, right? The other force is light pressure, which is caused by nuclear fusion. But again, let's be more specific on that. As the matter in a star, which is mostly hydrogen, but possibly some helium and a very, very little heavier elements, they're forced together in the star. So what will happen is, because they get forced together even like more and more and more, two hydrogens will join to form a helium atom, which is known as a proton-proton chain reaction. And this fuels a lot of the stars that we know of. The only other type of nuclear fusion is Carnot cycle, but that's a story for another day, right? So this kind of nuclear fusion produces a light pressure that pushes outward of the star, and that's the second force contributing to a star. So when these two forces, the force of gravity and the light pressure caused by nuclear fusion, when they balance each other out, that is hydrostatic equilibrium. So just wanted to make that very, very clear, right? So that's what makes a star stable. Now, the variability of a star is commonly presumed to be an imbalance of these two pressures due to the increase in nuclear fusion rates somewhere in the stellar evolution, but that is not quite accurate. There's a more complicated process to the pulsation of a star, which I'm going to mention right here. And to put it simply, it has more to do with the radiation of the star, but let's get into this step-by-step process. So, as put perfectly by the Australia Telescope National Facility, if the pressure outwards exceeds the gravitational force inwards, the outer layers of a star will expand outwards. As the star expands, its gravitational force inward diminishes because, again, there's more space, more distance, but its outward pressure also drops at an even greater rate because, like, the gas expands. And if you think about gas expanding, right, and there being like more volume, hopefully that kind of makes sense. Eventually, the star would reach a position at which hydrostatic equilibrium occurs, but the outward moving layers still have momentum, so they will resist a change in motion, and that momentum carries the layer past the equilibrium position. Then, as the gravitational force acts on the layer that is past the equilibrium position, it slows down. A point is reached where it stops, but now the outward gas and radiation pressure is weaker than the inward acting gravitational force. The imbalance of forces now causes the star's outer layers to collapse inwards, right? So we pushed it out with the gravitational force going down, but now it's coming back, right? As the layers collapse, gravity increases, but the pressure increases at a greater rate. With the pressure outwards exceeding the inwards gravitational force, the collapsing layer slows down and eventually stops. We are now back at the start, where the outwards pressure is greater than the gravitational force, so the pulsation cycle starts again. And hopefully that's making sense. But yeah, that's intrinsic variability for you. Now, semi-regular variables. They're pulsating variables, so they go through the process that we've just described, right? Where you get outwards, the moving layer comes back, but then everything else kind of collapses a little, and then it goes back to the start of the pulsation cycle, right? So that's intrinsic variability that is happening in semi-regular variables, but what differentiates semi-regular variables is their long periods of pulsation, one, their poor definition, two, and the stars that make them. And we'll get into all three in specific detail, but let's start with the long periods of pulsation. There is up to, you can get up to 2,000 days between each period of pulsation in a semi-regular variable, right? And that sounds small in the grand scheme of things, astronomy, astronomical numbers, they tend to get really big. But compared to other kinds of pulsating variables, these are actually huge numbers. So if we kind of limit our scope here to looking at only variable stars, it's 2,000 days is a pretty long period. Other variables like RR Lyrae and Cepheid, I believe is the pronunciation of them. I know I tend to say Cepheid, but it's Cepheid. Those variables typically have under 30 days of period length and under 1 magnitude of amplitude change, right? But the brightness of semi-regular variables in terms of amplitude changes 2 magnitudes. So these are different, right? And you have to consider that these stars are probably the largest stars that will pulsate to such a magnitude. You can get things like luminous blue variables, which we won't dig deep into, but they pulsate way less than semi-regular variables. So another thing about semi-regular variables is they have a big range, so they're separated into 4 categories, and we're going to get a little bit more into this poor definition thing as we look at some of these categories. So the first category is the A category, class A, which is MCS spectral classes, smaller, and they have smaller light amplitude than a mirror variable, which is also in this category of long period variables alongside semi-regular variables, right? So again, because they have longer periods than usual. So I mentioned MCS spectral classes, and that those might not sound familiar, at least the C and the S. So C as a spectral type has been used to categorize giant stars at the cool end of the spectrum that have an excess of carbon, which were previously known as R and N stars. But hold on, let's pause for a moment. That might sound an awful lot like a carbon star, which is what we looked at in the last episode when we were looking at RCBs and how funky their variability was, right? But let's hold off on that. Let's come back to that. We'll get to that in a second. S-type stars are just simply red giant stars. So they're kind of in this specific part of the HR diagram, and we'll talk a little bit more about that in just a second. There is a type B star for semi-regulars. These are basically the A-type stars, but they have poorly defined periods. And the type C and type D, which are the two other types of semi-regulars, are the types where the periods get really, really long, like very extreme, and the amplitude also gets very, very extreme, right? So we now kind of understand, these things have a big range. They get a little funky. It's a big group. So, they seem very poorly defined. What's up with this whole poor definition thing? If we look past the main pulsation of a semi-regular variable, you'll find what is known as overtones of pulsation. And the best we can do to describe these overtones is say that the star is most likely changing modes of pulsation, right? Because you in the process that we described earlier, you expect one single pulsation, right, where it goes out and then eventually it comes back in, right? But if you have these overtones that are kind of like getting in the middle of these main pulsations, really intuitively you can only say, well, it's likely that there's not just one big pulsation. There's like one and then a smaller one and then a bigger one, and it's a more complicated pulsation in that sense. So yeah, that's basically changing modes of pulsation for you. Described in slightly different words. If a star has multiple modes of pulsation, a second set of pulsations regularly occur in between the first set of pulsation. If not this, right? If not, it's changing modes of pulsation, then it's going through some sort of stellar evolution, which is less popular, but still somewhat likely. And the patterns that are present in these stars are shared by several stars, but we cannot point our finger at what this pattern is or put them in all in the same box, which is really just the essence of the poor definition of semi-regular variables. So we get semi-regulars, they're a little different from the others, poorly understood, whatever, right? But let's talk about one last thing. Remember the stars that make SRVs or semi-regular variables seem a lot like carbon stars? And the fact that I just mentioned that SRVs tend to blend in with other variables, right? That's no coincidence. SRVs are situated on the AGB, or the asymptotic giant branch, and that might sound very familiar from what we talked about in the last episode. They're cool but luminous stars, and they sound just like RCBs. So what is up here, right? I guess you could say we're starting to see a correlation between the instability of the asymptotic giant branch and the variability of stars like RCBs and LPVs, and that's what makes variable stars so interesting. We're beginning to see something accumulate in terms of stellar classification. We're starting to see a pattern between these really funky variabilities that seem to have a lot in common. If you look at an HR diagram and you put this on an HR diagram, you'll see RR Lyrae and Cepheids, which are the normal pulsating stars, follow this strip away from the main sequence that's called an instability strip. And more interestingly, if you look to the right of that instability strip, you'll find carbon stars that create long period variables like Mira and SRVs, right? So you've just found the asymptotic giant branch that creates carbon stars, that creates these funky kind of RCBs and long period variables. You're seeing that being justified by an HR diagram. And I think that's what's really cool about semi-regular variables, right? Even though we can't specifically say what an SRV is, we see how it fits into the AGB sequence with other variables. Like we can see a star evolve in a million different ways in retrospect, right? Considering how we've just found where SRVs belong on the HR diagram, we can see a star evolve in millions of different ways and see where it fits with the rest of the stars in our universe, and we can discover never seen before but phenomena like SRVs that don't even have a well-defined period at times. We can differentiate and correlate at the same time with an HR diagram. I think that's what's cool about semi-regular variables. Like, they're like an important piece to realizing some of the connections we can make in terms of stellar classifications. Like, since we see that semi-regular variables, even though they're poorly understood, seem to really jump in line with some of the long period variables that we already know, and some of the RCBs, we know where to put them in the HR diagram, and we were allowed to kind of make comparisons with some of the other variables that belong on a different part of the HR diagram. And it seems like from the way that I've put it, I think that SRVs have become a really, really important piece of figuring out the map of variable stars, like why we make differentiations between regular pulsating variables and long period variable stars. Why do we make a differentiation between intrinsic variability and extrinsic variability? Well, it's because from what we understand about long period variables like SRVs, we see they belong on a different part of the HR diagram, which means um, there's a difference, but there's also a correlation. So yeah, I thought semi-regular variables kind of helping us understand why stellar classification through HR diagrams is important. I thought that was really cool, and that's why I decided to research it. I wanted to look into ellipsoidal variable stars at first because of I thought it was really cool that gravity can kind of warp stars and make them variable, but I am more appreciative of the fact that I've researched semi-regular variable stars because in terms of what we've understood so far in the podcast, SRVs end up being one of the more important pieces to the puzzle in terms of stellar classification. So that is it for the podcast. I hope you guys have enjoyed listening. I hope this has some kind of relevance or significance to your astronomical understanding because it definitely helped me out a little bit. I've always had a little bit of difficulty kind of navigating the difference in variability stars and like why we tend to draw an instability strip across the HR diagram to differentiate variable stars from main sequence stars and why we have these crazy asymptotic giant branch stars and horizontal branches and red giant branches. It's all crazy, but I think it's nice to kind of look at this specific piece and say, "Hey, we don't know much about it, but it's really important because it helps us figure out some other stuff." So, yeah, if you're listening on Spotify, make sure to drop a follow if you enjoyed it. And if you're listening on YouTube, I would really, really appreciate a subscribe. And until next time, I will see you guys later.